Yeah. Hello to everyone. I'm Kenny, and I would like to give a talk that is going to be about a comparison of vector symbolic architectures. Um, I'm a part of the professorship process automatization, and we are with the Chemnitz University of Technology, Germany. And yeah, for a better overview, my colleague Per Neubert gave a talk in the last summer session of the VSA webinar series about the hyperdimensional computing in robotics and the comparison of VSAs. The talk was mainly about the robotics application, especially the visual place recognition task. And at the end, he gave an outlook about our results of the comparison of VSAs. And yeah, today I would like to take a closer look at the last point, the results of our comparison of vector symbolic architectures. And yeah, that's by the way. Let's start. Yeah, why a comparison of VSAs? I will explain it on our own experiences. For example, yeah, we had the problem to solve, maybe the visual place recognition task. And we found the method of VSAs or HD computing and want to solve the problem with a VSA, but several questions arise. For instance, are there several different VSAs? Do they have different properties? Which one is for my application the best choice? Or how can it be implemented? And especially for newcomers in this, the field is difficult to survey. And that's why it is important to know the answers to these questions. And yeah, that's why we try to systematize the different implementations of VSAs. And yeah, this is part of our paper, which is available on arXiv as in preprint. And we are also planning to submit the paper to a journal within the next week. And on arXiv, there's an updated version. So the already existing version on arXiv was extended by some practical experiments. For example, the visual place recognition task. Okay, now let's see what we have done in our comparison. First, yeah, we explained the different VSAs and their property, their operators, and their differences and commonalities. And yeah, the outcome of this first point was that certain binding operations can have important ramifications for some applications. And yeah, by the way, I will highlight some important findings and outcomes during the talk with such yellow sticky notes. So they can also be seen like take-home lessons or so on. Yeah, that's by the way. Our second point is based on synthetic experiments on the bundling and binding operation. The outcome of this point is that some VSAs show unexpected and significant results. Our third point is regarding practical experiments on the language and visual place recognition task. There we figured out that the synthetic results of our second point are mainly transferable to real-world applications. And the last point, there we provide an implementation of all VSAs, and that can also be used as a MATLAB toolbox. And yeah, the toolbox provides a simple and test environment for all VSAs we evaluated in our comparison. This slide can also be seen as an outline for the following talk, and I would like to tell something to each point individually. Okay, let's go to our first point, the different used VSAs. As you can see, we evaluated and compared a couple of VSAs. They are mainly categorized into real, binary, bipolar, or complex vector space. And yeah, we summarized some properties based on these categories within such a table. Yeah, this is just for an overview. More details can be found in our paper, but one thing has to be said. Since the bundling operator is almost the same for all VSAs, it's just element-wise addition. The binding operator differs sometimes a lot for several VSAs. And yeah, that's why we created a taxonomy to systematize this specific operation. The result can be seen in the on this slide on the left side. There we can mainly divide the binding operation into multiplicative and additive operation. And the multiplicative operation can also divide it into self-inverse and non-self-inverse binding operation, both with approximate and exact invertible bindings. And yeah, why is it important? Well, it implies possible ramifications for applications like the what is the dollar of Mexico example. I think everyone in the audience know this example. Yeah, it consists mainly out of two representations. For example, one for the country Mexico and one for the United States. And based on the algebra of vector symbolic architecture, it is possible to calculate the answer to the question, what is the dollar of Mexico? But yeah, but this is only possible with self-inverse bindings. Also, the self-inverse property is necessary for solving these tasks. And even if the unbinding operator for non-self-inverse VSAs will be used, the equation cannot be simplified to the result, as you can see in the notes on the slide. And such VSAs with non-self-inverse binding require other strategies to solve such tasks. And yeah, we think such an insight is also good to know and very interesting, especially for a newcomer within this field that tries to apply a VSA to a similar problem. And that's why the take-home lesson from our first point is that certain binding operations can have important ramifications for some applications. Okay, let's go on to our second point, our synthetic experiments. These experiments are mainly divided into 3 sub-experiments. First, to evaluate the bundling capacity with the question, how efficiently can the different VSA store or bundle information into one representation? Second is based on the approximately invertible bindings with the question, how good is the approximation of the binding inverse? And the third experiment is a combination of all 3 operators together, so with binding, bundling, and unbinding. And the question to this is how many property values or will filler pairs can be bundled and still provide the correct answer to any query by unbinding a row. Within this talk, I only concentrate on the first and the third experiment. And yeah, if someone is interested on results from the approximately invertible bindings, please refer to our paper. Okay, then let's see the results from the first experiment, the bundling capacity. Yeah, to answer the question, how efficiently can the different VSA store or bundle information into one representation, we did an experiment as follows. We have, for example, an item memory with some elemental vectors. Each vector is randomly chosen, and we select a predefined number of vectors out of the item memory, for example, k vectors, and bundle them together. And now we compute all similarities to our elemental vectors and select the k highest. And this selection should be the same as at the beginning. And based on it, we can compute an accuracy of a perfect retrieval. And yeah, we apply the experiment with various numbers of dimensions and number of k vectors or number of bundled vectors. And yeah, for this, it has also been noted that we only consider the number of dimensions and not the storage capacity. This will be a separate topic and is out of the scope of this presentation and this comparison. Okay, let's see the result of this experiment. It can be seen in this plot. It provides an evaluation of the minimum required number of dimensions to achieve almost perfect retrieval for all for different values of k or different number of bundled vectors. And it can be said that the shallower the lines, the less dimensions are required to store the corresponding elemental vectors. And yeah, the better is the capacity of the VSA. Yeah, for a better overview, here you can see the different vector spaces from binary, real, and also the complex or sparse binary vectors. And yeah, as expected, the binary vectors needs more dimensions as, for example, the real valued vectors. Yeah, because the binary vectors has a smaller range of values with only zeros and ones. Interesting is the result of the complex and sparse binary architecture. Both yeah, requires only a few dimensions to store the different number of bundled vectors and has a high capacity. And especially the second point, the complex domain is very interesting because complex VSA or complex VSA vectors contain only the angles of the complex numbers as real valued numbers. So this is an assumption of the complex VSA. And so we can conclude that if real numbers are treated as if they were angles of a complex number, then this increases the efficiency of bundling. So this is a quite interesting and important outcome from this experiment, and yeah, leads to this take-home lesson. The summaries A show unexpected and significant results, especially the complex VSA. Okay, now let's see an extension of this experiment, expand the bundling by binding and unbinding, so all operators together. To do so, we did an experiment similar to one of the experiments from the book How to Build the Brain from Elias Smith. For this experiment, we also have an item memory with elemental vectors. And from this item memory, we bind vectors to k pairs. And these pairs are bundled together into one representation. And now we try to retrace the elemental vectors from the result by unbinding one of the original vectors. For example, if we want to retrace the vector A1, we have to unbind B1 from our complete bundle. Yeah, for this experiment, we also vary the number of dimensions and the number of bundled pairs. The result can be seen in a similar plot to the capacity experiment. And here, each line represents one binding type of a VSA, and the same goes for here. The shallower the lines, the better is the performance of the VSA. And yeah, the many lines can complicate the overview. That's why we evaluate the VSAs by comparing their accuracies to those of the capacity experiment as follows. On the left side, we have our results from the bundling capacity and select the minimum required number of dimensions to retrieve the 15 bundled vectors. And we select from the last experiment the minimum required number of dimensions to retrieve 15 bundled pairs. And the question is, does the capacity change if bundling is extended by binding or unbinding? It's like a binding and unbinding under noise, and the noise comes from the bundling. Yeah, the results are summarized in the table below, and the second column is regarding the bundle capacity experiment, and the third regarding the last experiment. And it can be also seen the increase of number of dimensions between both experiments. And here, most VSAs has almost no changes and are within the bounds of ±5%. And this means that the binding and unbinding operator is robust against noise. And as I mentioned at the beginning, the noise is caused by bundling of the pairs. And noticeably is that there's a significant rise of number of dimensions for the last sparse binary VSA, and the binding of sparse vectors in combination with bundling requires more dimension, as you can see, up to 44% more, 1% larger vectors. Okay. These are the results of our synthetic experiments, and now we want to figure out the performances on practical experiments, and there we evaluate the VSAs on the language recognition task, as well as on the visual place recognition task. And we try to answer the question, are the insights of the previously seen synthetic experiments transferable to the real applications or the practical applications? Now let's try to answer this question based on the language recognition. For this, we did an experiment similar to the reference one. And the goal of the language recognition is to recognize the language of a given text. For this, each letter is represented by randomly chosen hypervector, and to construct a meaningful representation of the whole language, short sequences of letters are combined in n-grams. And the learning or training of a language is simply done by bundling all n-grams of a training data set. And for recognizing the language of a given query text, the same procedure as for learning is repeated, and the nearest neighbor query with all known language vector in the item memory is performed. And for this experiment, we also vary the number of dimensions, and the result can be seen on this slide. So we try to figure out the efficiency, so which VSA need only few dimensions to reach high accuracy. And here also, for better readability, the faster the curves have a high accuracy, the better is the performance and the better is the VSA. And the result is that the complex and the matrix binding VSA show good results, and similar to our synthetic experiments, or to the results of our synthetic experiments. And that's why we can say, okay, for the first practical experiments, the results are mainly transferable to real-world applications. It's based on the results, for example, from the complex VSA, it shows in both very good results. And let's see how it is for our second practical experiment, the visual place recognition task. I do not explain the visual place recognition in detail. For this, I would like to refer to Per's talk last time. But nevertheless, we have to encode our, for example, images into descriptors according to specific VSA vector space. And based on these image descriptors, we apply two different methods. First, the state-of-the-art method from sequence_lem for visual place recognition, and the sequence_lem as a VSA implementation. So as it's like an approximation of the original sequence_lem with a VSA. Why a VSA is an approximation? The VSA approach has the advantage of only requiring a single vector comparison to decide about a matching, while sequence_lem typically requires 5 to 10 times as many comparisons. So you can see a VSA can be more efficient than the original sequence_lem method. And with the results for both, we compare the results and try to answer the question, how good performs the VSA approximation compared to the original sequence_lem method? And our results, we summarized our results within a table. You can see we evaluate all VSAs on 5 different data sets. each with several database and query images. And yeah, we write down the results as follows. For example, we have VSA. Then we apply for each VSA type or each VSA encoding the original sequence limb method as well as the VSA approximation. And yeah, write down the results column-wise. Yeah, we did this for each VSA, and yeah, the resulting table is yeah, like this. For better readability, we add some colored arrows, green, yellow, and red arrows. A green arrow means that the VSA approximation is able to reach the same performance as the original sequence limb method. And yeah, red arrow means the VSA is not able to approximate the original sequence limb. And yeah, as you can see, for example, the real valued map architecture is able to reach for all data sets the performance of the original sequence limb, and as well as the matrix binding VSA reach also good results. The other architectures like the revalued HRR as well as the complex architecture have also good results with only 1 or 2 yellow arrows. So the same goes for this experiment as compared with the language recognition. The synthetic results are mainly transferable to the real-world applications. So yeah, that's the outcome of our practical experiments. Okay, the last point is regarding our MATLAB toolbox or our implementation. As I mentioned at the beginning of the talk, we provide our source code, and that can also be used as a MATLAB toolbox. To explain it very shortly, for example, you can initialize a different VSA environment with a specific type. The types are all VSAs we evaluated and compared in our work, and you can add some vectors to the item memory. You can apply bundling, binding, and unbinding with this environment, and can also compute similarities between vectors, and can use the cleanup memory, or you find the k-nearest neighbors out of the item memory. And yeah, as you can see, it's very simple to use this MATLAB toolbox. And yeah, it has to be noted that this implementation is not as fast as possible, but yeah, it provides rapidly and easily testing of the different VSA types. And yeah, such a simple toolbox can be also beneficial for rapid prototyping of an application with a VSA. Okay, at the end, I would like to summarize the important insights of our comparison. Yeah, the first was that certain binding operations can have important ramifications for some applications. Remember the taxonomy of our one of the first slides. The second is that some VSAs show unexpected and significant results. Remember to the bundle capacity experiment. And yeah, our synthetic results are mainly transferable to real-world applications. And yeah, some VSA vary a lot and some are better suited for specific tasks. And yeah, this has to be taken into account for selecting the best VSA. And finally, there our MATLAB toolbox. And here we hope that this systematization has created a better access to this topic and that the best possible VSA can be selected for an appropriate application. And yeah, that's it. Thank you for your attention, and information as well as the code can be found on our webpage. Yeah, thanks.
All right, thank you, Kenny, for the great talk. So our applause goes to you. All right, so we have some minutes for questions, reflections, comments. Anybody?
I have a question.
Go on.
Kenny, could you please go to slide 15?
Yeah. slide.
Yeah, so here, the last two VSA frameworks, what is their difference?
The difference between the both
Yeah,
experiments?
the last two binary sparse distributed codes.
SEG.
One is with
okay.
SEG.
Yeah, the difference between
the one with S.
this architecture is the binding operation. So the last sparse binary uses a simple shifting of director for binding, and the first sparse binary used these segment-wise operations. So the complete vector is divided into is shift by defined number based on the other vector of the bundled pair.
I think, thanks.
I have a question.
Go on, please.
Have you? I think it will be interesting to measure this capacity, but also considering the memory space of the BCAs, because the binary vectors will use maybe 1 bit or maybe 8 bit for each component, but the real vectors are going to take like 32 bits or even 64 bits of information. So it is a bit unfair, the comparison, but it makes sense, the results.
Yeah.
But I think the memory capacity should also be considered.
Yeah, that's true. That's also an important point in memory capacity, because as you mentioned, the binary vectors needs only a few bits or only 1 bit per dimension, and the real vectors need some more. That's why I give the hint of that we only consider the number of dimensions and not the storage capacity. And it's also important to consider the memory capacity. Yeah.
Thank you.
I think here, just to be clear on the terminology, I think here we mean the memory footprint of the reactor. So there is a comment by Chris Simkin in chat, which is rather valid. So a 100-dimensional 64-bit real reactor is equivalent to 66,400 bits binary reactor. So talking about dimensionalities, you should take into account the dimensionality of each position.
It's also related to this previous question of the storage capacity, right? So the difference of number of dimension and the required bits to represent the hypervector, right?
Yes.
Yeah, this is also important that maybe for the future to extend the experiment of the bundle capacity with considering to the storage capacity, maybe by normalization of the results by the storage capacity of each vector space. But it's not. It was not part of our comparison for at this point.
Sure. Any more comments, questions?
I would like to say something.
Yes.
And that is, you talked about permutations as a part of the example in language recognition, but you really didn't compare permutations in your various things. That's something that you could do in the future. Extend your table. I mean, you have been using what the addition and multiplication do, but then how do these various kinds of architectures respond in terms of permutation? Because I think permutations really are a powerful thing to add into this. This is something that Ross Schlegel really brought home to me, and ever since I've been a real fan of permutations.
Yeah. Yeah, that's true. We assume the permutation as a circle shifting of the vectors, but yeah, so we assume it for all VSAs as a circle shift.
Good. Yeah, the number of permutations and the algebra permutations is incredibly rich.
Yeah.
And we really haven't explored that hardly at all.
Yeah. That can also be a topic for your future work.
Well, thank you.
Yeah. Thanks too.
Okay. I guess if there are any other questions or comments, please send them, communicate them via our VSA community mailing list. So you can find the mail address in the invitation email. Also, Ross is writing his comment, so just not to forget about his comment. I think Tony Plate showed that real representations only need very low resolution, so it might be better to think of reals as only 4 or 8 bits each. Yeah, well, it's also valid. Right, but once again, thank you for attending this first session of winter session of our webinars. Thank you to great thanks go to our 2 presenters, Peter and Kenny. And we see each other in 2 weeks from now, and I can give you some heads on that the webinar will be scheduled 3 hours earlier. So, and it will happen at 6 p.m. Central European time. So on 30th of November. So, but I will come back about this issue in my next email. All right. Thank you very much for attending. Great to see you all. Bye. See you next time.
Thank you.
Thank you, everyone.
See you.
Bye.
Bye.